Okay.
How you doing?
I'm doing good. How are you?
All right.
You're gonna get a private audience. My question's gonna go up. I didn't charge extra for this.
Okay, we're going to go ahead and get started. Can the people on Zoom hear me okay and see the slide?
Yes, we can.
Can the people on Zoom hear me or you see the slide?
Yes, we can.
I'm going to guess that's a no.
We can hear you. Can you not hear us?
Okay, so you can hear me, but I can't hear you. All right. Thank you. Don't know why that is, but we're going to go ahead and get started. If you do have a question or something, just type it in and I'll hopefully check that and see it. So what we're going to do today is we're going to finish up chapter 17. And then on Thursday of this week, we'll have exam number 3, and that covers chapters 15, 16, and 17. As usual, the exam will be in Canvas, and it'll be during the class period, so no need to come to class. Just find a good place to take the exam and take it during the class time. All right, so chapter 17, we left off, we had talked about the Henderson-Hasselbalch equation, and we're talking about buffers. And so one property of buffers that is important is buffer capacity. And what buffer capacity is, that's just an indication of how much acid or base a buffer solution can handle, in other words, neutralize, without there being an appreciable pH change. There's always a tiny bit of pH change when you add acid or base, but usually it's pretty insignificant if the buffer is in the proper range and the proper concentration. Another kind of example of buffer capacity is if you have a conjugate acid base pair and the concentration of each is 1 molar, versus that same conjugate acid base pair and the concentration is 0.1 molar, well, the pH would be the same based on that Henderson-Hasselbalch equation. But what you would find is the 1 molar acid base pair would be able to handle a lot more acid or base coming into the solution and maintaining that pH than the 0.1 molar would be. So buffer capacity is a big deal because it gives you a feel for how much acid or base a solution can handle. pHs are important because a lot of reactions occur at a particular pH, and this is a way by buffering the solution, you can ensure that the reaction stays at that pH. And by converse, sometimes you want to break that buffer, and it's nice to know how much you need to add to do that. Buffers also have a pH range over which they are effective. And basically what that range is the pKa plus or minus 1. And that comes from that the optimal pH is when pH equals pKa, or in other words, you have the acid concentration equal to the anion, the conjugate base concentration. So when you think about when you set up a buffer, you tend to have that conjugate acid base pair have concentrations that are pretty much the same or close to it. And then if that concentration ratio gets out of whack by, say, 10x or more, then the buffer isn't as effective and doesn't work that well. So the rule of thumb is that if you know the pKa of something, so say you have a weak acid and you know the pKa is 5, then you would say that that can serve as a buffer anywhere from pH 4 to pH 6, so plus or minus 1 on that pKa. You get outside that, and what you find is that the buffer just doesn't work that well. So a lot of times when you're trying to figure out what buffer you would use for a system, you would go to the pKa tables and say, well, if I'm trying to maintain something at a particular pH, which pKa is closest to that pKa? And that's how you would choose the weak acid, for instance, that you would use. So if you have a buffer system And then either a strong acid or strong base is added to that buffer, you're going to get neutralization of the acid or base. And so the way to think of that is that that strong acid or strong base gets put into the buffer system, and then it's going to get consumed. And so you're going to neutralize that acid or base, it's going to get consumed. And then you can calculate what impact that has, if any, on your buffer system. And so when we do these type of calculations, it's very similar to the other equilibrium type calculations that we've been doing. And hopefully you're kind of seeing that trend as we've worked on equilibrium for a while now, that even though the different constants have different names and things like that, the basic idea is pretty much the same every time of what we're doing. And that's the same here. And so let's look at an example of this. So here we have a buffer that has 0.3 moles of acetic acid and 0.3 moles of sodium acetate. And we're going to make a solution that's 1 liter total volume. And so what we want to do is then calculate the pH after we add 0.20 moles of sodium hydroxide. So our weak acid is acetic acid. So we have that acetic acid, acetate ion buffer system. Our concentrations are both 0.3 moles. So that's good. Those concentrations are pretty similar. And then we're adding a strong base, in this case, 0.020 moles of sodium hydroxide. So let's see what happens. Well, we're going to set this up as we normally would with kind of what I'll call our equilibrium table, where we have the reactants and then the products. So acetic acid, hydroxide are the reactants, and then excuse me, acetate is the product. And so in this case, we start out with 0.3 moles of the acetic acid and 0.3 moles of the acetate ion. And then we're adding 0.02 moles of the hydroxide. So when we look at what the change is, that 0.02 moles of hydroxide is going to react with the acetic acid. So that's minus 0.020 for the change of acetic acid. The hydroxide, we said if it's a strong acid or strong base, it's going to get all neutralized. So in this case, we started with 0.020 moles. So now we're going to use up 0.02 moles. So we list that as negative 0.02. The LR stands for limiting reagent. That just means that, as we've talked about limiting reagents in the past, that's the one that's going to get used up totally. There's not going to be anything left. And finally, the acetate concentration, if the equilibrium is shifting 0.020 moles of acetic acid, if we're using up that much of the acetic acid, then we're going to form that much of the acetate ion. So then if we rebalance things in our last row, we see that 0.3 minus 0.02 is 0.280 for moles of acetic acid. Hydroxide is all used up, so that's 0. And then the acetate is 0.320. So now we have concentrations for our anion and then our acid. So we can put those into our Henderson-Hasselbalch equation. Remember that was pH equals pKa plus the log of the concentration of the anion divided by concentration of the acid. We go ahead and put our values in that we just calculated. So 0.320 divided by 0.280, take the log of that. The pKa we could look up, or we could look up the Ka, and if it's pKa, then we would do what? We would do minus the log of the Ka, and we get a value of 4.74, and then we go ahead and do that math, and we see that the resultant answer is 4.80. So let's take a look at kind of get a feel for what the effect of a buffer is. Because you think about it, we talk about having a buffer and adding acid or base to it, we don't get much change. But what would happen if we didn't have that buffer there? And this will give you a feel for why buffers are so important. So in this case, we're going to take a look at adding a strong base to buffer and adding a strong base to water. So let's look at the water example first. We're going to take 5 mils of 4 molar NaOH and add it to 1 liter of water. What's the first thing that we would do? We would think about what that neutralization reaction is, right? And so it would be sodium hydroxide going into the water, and now you've got a bunch of hydroxide forming. So if we want to find out how many moles of hydroxide, we know it's 4 molar. We know it's 5 mils. We need to convert that 5 mils into liters because molarity is moles per liter. So 5 mils is 5 times 10 to the minus 3 liters. I multiply that value times the 4 molar, and that tells me I have 2 times 10 to the minus 3 moles of hydroxide. That's how much I've added to 1 liter. Well, if I want to find out what the molarity of that is, I need to take that number of moles and divide it by the total volume. I started with 1 liter of water and then added 5 mils of the base. So my total volume is 1.005 liters. So that represents the 1,000 mils from the water and the 5 mils from the base, and then expressed in liters. I do that math and I get 0.00199 molar hydroxide. Well, I said I wanted pH, right? So if I do minus the log of the hydroxide concentration, that gives me POH, and that value is 2.7. I also know that pH plus POH equals 14. So I can subtract this 2.7 from 14 and get a value of 11.3 for my pH. So this is what's telling me is the new pH of my water solution when I've added the base to it. Well, we always say theoretically water has a pH of 7, so let's stick to that. And so what it's telling me is adding just 5 mils into a liter of water, 5 mils of this base, change my pH from 7 to 11.3. So a pretty big pH change. Now let's take a look at what would happen if we added that same amount of base to a buffered solution. In this case, we have an acetic acid buffer solution. So we have, we're told that 0.3 moles of acetic acid, and then then we have 0.3 moles of acetate. We know from our previous problem that it's 2 times 10 to the minus 3 moles of hydroxide. Okay, so that part hasn't changed, so we don't have to recalculate anything. So all we have to do is subtract that from the moles of acetate, because we know that's going to get neutralized by the acetic acid. And then it's going to produce that number of moles of acetate ion. So our 0.300 moles of acetic acid now is 0.298. Our 0.30 moles of acetate are now 0.302. So the acetic acid's gone down a little bit, the acetate's gone up a little bit. I can plug all this stuff into Henderson-Hasselbalch. So I have log of 0.302 divided by 0.298 here on the right-hand side. Left-hand side, it's pKa. Acid dissociation constant is 1 times 10 to the minus 5. The P function tells me I take minus the log of that. So I can go ahead and do that calculation, and I get a value of 4.75. Well, we're told that the original buffer concentration was 4.74. So we see that there's a tiny change by adding this base. It went from 4.74 to 4.75, but not really much. That's not really very significant, especially when I go back and look at what happened when it was just water, and I went from 7 to 11.3. So this is why buffers are important. It allows a solution to maintain whatever that appropriate pH is, even when other things are introduced, okay? And the buffer capacity, that's important because something that has a stronger, higher buffer capacity, a stronger buffer capacity, can handle a greater disruption, and then it keeps the pH. If you think about biological systems in particular, there's reactions going on in biological systems. Those reactions are usually pH dependent. And so usually there's some type of buffer system in there so that as different things interact, it doesn't throw it off the correct pH and the reaction can go as planned. So when you're talking straight chemistry or biochemistry or biology or whatever, buffers always play a real important role in maintaining the appropriate pH for whatever process you're trying to carry out. Okay, so we're going to move away a little bit from the buffers, but we're still going to be talking about equilibrium. And so we're going to talk a little bit about titrations. Now, I know last semester in lab did a titration. This semester, I think you guys have done some titrations. So hopefully none of this titration information will be new to you. Hopefully it'll be just a refresher on some of this stuff. And if you think about the titrations we're going to talk about acid-base titrations. There are other kind of titrations. I know in the last class, someone told me you guys are doing redox titrations right now. So that's a little bit different. But we're going to talk today about just the acid-base titrations, strong acid-base titrations and some weak ones as well. But there's a whole bunch of other titrations out there as well. In our example here, what we're talking about, either you're using an acid as the titrant, and you're trying to determine how many moles of base are in the solution, or vice versa. And there's two main ways that you can tell these types of titrations when you reach that equivalence point. One is by having a chemical indicator where you see a color change when you get to the appropriate equivalence point. The other is to do a potentiometric titration, and that's where you usually, not always, but usually have a pH electrode in there, and you just measure the potential and you plot that versus volume. I asked the last class this, I'll ask you guys, which do you like better? The visual indicator, chemical indicator type titrations, or recording pH or potential, however you want to think of it? You like the color one better? Okay. How about you, Copper?
The visual one.
The visual one. Okay, last class, no one voted for visual. They all voted for potentiometric. So that's interesting. Most people like the potentiometric better because it's easy to make mistakes on the color. You add a little too much, and the next thing you know, it's not light pink for, say, phenolphthalein, for instance. It's dark pink and all that. Whereas with this, you just keep plotting, and you can do your plot, and you can get it after the fact. I'll tell you, anymore, people don't do the, other than in Gen Chem lab, don't do the color titrations very often. It's almost always potentiometric pH. Okay, so if you are using that pH meter or the indicators, when you get to the equivalence point, that means you have equal amounts of acid and base. And that's usually what you're after in these titrations. Yes.
I know that when we graph the equivalence point in our titrations, it goes like 4 to 11. Is the equivalence point between the 2 points, or is it when it, or is it like you added 24 milliliters, and when you get 25, it goes up to 11? Is 25 the equivalence point, or is it between the two?
So if it's an acid base one, a strong acid, strong base one, it's at pH 7. That is, and what pH 7 should be is like on this example that we see on this plot. You see how it kind of goes slowly up, and then it's real sharp up, and then goes slowly up again. If you draw a line along there, it should be right in the middle of that line. That's in theory. Now, whether you get that experimentally, that's another story, but that's, and for the strong acid base ones, it should be at 7. We'll see in a little bit that for the weak acid base titrations, it's not at 7. Like weak acids, it'll be up here higher, and depending upon how weak it is, the higher it goes up. But for strong acid, strong base, it should be at 7. It should be, if you draw this line along that straight part of the curve, it should be straight. Now, reality is it doesn't always look like that. But in theory, it should, and then it's in the middle of these two here, and that tells you the pH, and then you drop it down to get the mils. And of course, the mils is what you use to calculate to get how much acid in this case would have been in there. Does that make sense? Okay. So, once again, on this type of strong acid, strong base titration, so you have a strong acid titrating with a strong base, you're starting with a strong acid because you're down here pH roughly 1. It looks like on this, it's kind of a slow pH change. Maybe you have 1 pH change unit until you get near that equivalence point, big jump in the pH. Then now basically it's all base that you're adding, and it kind of flattens out again. So, and then halfway up in that middle point, that's your equivalence point, as I said, for these strong acid, strong base, it should be pH 7 in theory. If you do titrate a strong base with a strong acid, it just kind of flips that over, but the same idea. Here you started with a strong base because your pH is up around 13 on the plot. Stays not much of a change until you get near that equivalence point, then a big drop as you neutralize everything. And then basically you're at just the acid point here as you add more acid. So same idea though, pH 7 should be your equivalence point, and then you would extrapolate down from this midpoint of the straight part of the curve to get your mils of acid in there. So strong acid, strong base, those are the pretty titration curves. You get to the weak ones, it's not as easy to pick out the equivalence point always, because you don't have this nice big break like you get with the strong acid, strong base. And we'll take a look at those in a little bit. Okay, so if we titrate a weak acid with a strong base, we can use the Ka to find the initial pH, and we can find the pH in the buffer region, what we'll call the buffer region, because remember, if it's a weak acid, it has some buffering ability. And we can find the pH in the buffer region using stoichiometry and then that Henderson-Hasselbalch equation if we wanted to. The equivalence point, the pH will be greater than 7. And you could actually calculate that out if you use that conjugate base to determine what that pH is going to work out to be. You can certainly try and calculate it out. Normally people just do the titration and just see what it is. As with all titrations, moles of base add equals moles of acid. Okay, we're assuming in this case a 1-to-1 ratio from the stoichiometry. But the conjugate base, so the anion, the conjugate base of that weak acid is a weak base. Remember, weak acids, their conjugate is a weak base. So that weak base reacts with water to form some hydroxide. And that's the reason why the pH will be higher than 7, okay? When you do that neutralization, take acetic acid, for instance, you have acetate ion. Acetate ion is a weak base, so you do get some OH generated. And the amount of OH will depend on what those pKa's are. So we look at a curve for a weak acid titrated with a strong base. And a couple things I want to point out on here. We see this initial. So we're starting here, it looks like it's about a pH of about 3. We're starting out and we see that that is a little bit greater slope, that portion of it, than we have with the strong acid, strong base. We also see that our equivalence point is, I don't know, maybe that's 8.5 or so, but it's definitely above 8. And it's definitely above pH 7. So with the strong acid base, we had equivalence point was going to be at 7. But here, because of that acetate being a weak base, we wind up in this equivalence area of being above 7. So we would find that equivalence point by drawing this perpendicular, that's the dashed line you see going down through that straight portion of the curve. Now, you'll also notice that that straight portion isn't as big as it was on that strong acid, strong base curves. And this is why I was saying, as we get to even weaker acids, that portion is even smaller, and it gets a little trickier even to kind of figure out where the best parts are. That's why the strong acid bases are the pretty ones, because you get that nice, longer, straight area. It's easier to figure out where the equivalence is. So there you have that equivalence point there, would be in the middle of that straight portion. And like I said, in this case, because of the acetate having some, acetate ion having some basic properties, you wind up with the equivalence point being above 7. So when we do something like this, we do similar calculations like we've done before. We do this titration, we calculate the moles of weak acid, we calculate the moles of base added, and this moles of base added will also be the moles of acetate that's formed if it was acetic acid. And then we can subtract it from the moles of acid to see how much acid is left. And then if we wanted to find the pH there, we'd use that Henderson-Hasselbalch equation to find the pH. And so we'll work through an example of this. I think it's in the homework. So let's take a look at these weak acid titration curves for a second. We looked at one, now let's look at some others. And so on this graph that we have here, we have on the dotted line the equivalence point, okay? And down at the bottom, we see strong acid, and then we have Ka values as we go up. And we see they range from 10 to the minus 2 to 10 to the minus 8. So 10 to the minus 8 is going to be the weakest acid. Because remember, acid dissociation constant, that's products over reactants. If that ratio is small, it means we didn't form very many reactants. So that's the weakest acid. And what you see here is a few things. One is, as the acids get weaker, we see the starting point of that initial pH becomes more and more basic. Okay, they're all still acidic, but the top one is, I don't know, maybe that's 4.5, 5, something like that. But we see that pH getting values getting more basic. The other thing you see is you look at the area where that equivalence is occurring. And by the time you get 10 to the 8th, boy, there's not much of a straight portion there. You get to that one, it's kind of tricky figuring out what that equivalence point could be. I mean, there's one picked here, but if we're following our kind of process that we talked about with the strong acid, you've got that nice straight portion, just draw a straight line through that. This 10 to the minus 8 one doesn't have a lot going on there. There's not a lot of straight portion, so it gets a little trickier. And so what you see here is that straight portion diminishes as the Ka is smaller, okay? And this pH change, what that means is the pH change in that region is less And that goes back to buffering and things like that. So the titration curves are going to look a little different depending upon what you're titrating. Once again, strong acid, strong base titrations, those are the ones that look like kind of the classic titration curve. You get to some of these weaker acid ones, and then they don't look, they're not quite as clear, I don't think, of seeing where your equivalence point is. So we talked about there's a couple ways we can do the titrations. And one is indicators, chemical indicators, and the other is using a pH meter or something that measures potential. Well, indicators are simply, they're usually weak acids, but they're simply chemicals that as they go from acid to base or base to acid, that they change colors. And there's usually a finite pH range over which that happens. And so if you are looking for an equivalence point in that range, then you can use that color change to tell you when you get to the equivalence point. But you got to pick the right indicator. If it's changing colors on an area that isn't the equivalence point of your reaction, of your titration, then it doesn't really do you much good. The other thing about indicators is, it says here we want changes of color in small volume change region, okay? And you do. You don't want to have to add 10 mils in the region to get the color change. You want, but that's good. It's also bad, because if you think about, for instance, last semester when you did the phenolphthalein acid-based titration, it's real easy to go from light pink to dark pink. It wasn't even a drop for most people. And so you think about that, it's like, wow, that's a lot of pressure to get the exact amount in there. So you want something that changes like that, but at the same time, it's easy to overshoot. And that's really one of the reasons why people often will use the potentiometric pH type monitoring. Okay, so this is just some visual of picking the right indicator. So over here on the left, we're saying for phenolphthalein indicator, that works over 8.3 to 10, okay? But this equivalent, we have some equivalence points here that people are looking at, and none of the equivalence points show up. None of the equivalence points show up in the area. So the equivalence point we see looks like it's, I don't know, maybe that's a little over 5. And our change doesn't occur until 8. So if we're trying to find the equivalence point at 5, we're not going to get it with an indicator that changes in this 8 to 10 range. Now, if we go in, this other indicator is called methyl red, and it's saying that color changes between 4.2 and 6. So we see there that pH, that equivalence point being around 5, is right in the middle of 4.2 to 6. So that tells us this is a reasonable indicator to use for that. So that one of the problems with that is if you don't know where the equivalence point is, seems kind of funny, doesn't it? You got to know the equivalence point before you do the titration for the equivalence point. Yeah. So obviously it would have to be something where it's not the first time you've done it, that you know what it is, and now you have a bunch of samples to do, and that's how you pick your indicator. Okay. Let's talk a bit about polyprotic acids. So hopefully everyone remembers what a polyprotic acid is. Polyprotic acid is an acid that has more than one proton that can be donated. So examples would be sulfuric acid, H2SO4, has 2 of them. Another common one is phosphoric acid, H3PO4. So there you have 3 protons that actually can be donated. With the polyprotic acids, for each of those protons that can be donated, they have an acid dissociation constant. So that's where you have the Ka1 or pKa1, pKa2, on down the line, depending on how many protons you have. In this example here, we have a diprotic acid. So we have two acid dissociation constants. And so what you do when you titrate those is, it kind of goes along. Here we have our first equivalence point here at about 50 mils. Looks like that pH is probably a little over 4. But you can actually get what the pKa of that is by going to the equivalence point to where you started and picking half that volume and then extrapolating over. So in this first one, the pKa is probably about, I don't know, that's probably about 1.8 if we do that exercise. The second pKa, we would say, okay, so 50 mils was our first equivalence point. We continue titrating. We determine our equivalence point is, I guess that's probably about pH 11 there. That's a case of where personally, I think it should be a little lower if you just look at where that is on that. This is where it gets a little, subjective. But let's go with what is on the graph and say pH 11. We drop that down to 100 mils. Well, now we have 50 to 100 mils is how much we titrated to get from that first equivalence to the second. So that's 50 mils. Half of 50 mils is 25 mils. So if we look at 50 plus 25, that's 75. We go up to there, and that's our pKa2. We extrapolate over to the pH thing, and it tells us our pKa2 is, I don't know, maybe 6.2 or something like that. So on these polyprotic acids, you can get multiple equivalence points, okay? If it was phosphoric acid, a triprotic acid, then we just have another one of these. And you can also, by looking at where you start versus getting to an equivalence point and then going halfway in between that, you can get pKa values for the different protons that are being donated. So this type of titration like this, to get these pKa values is actually pretty good. This is done quite a bit because you're doing the titration because, to be honest, you're not that concerned about what the exact equivalence point is usually, but pKa values, people are always interested in those because pKa values are used to understand the ionization of the compounds. And we'll talk about that a little bit later this morning. But pKa values, you always are interested in those, and that's one of the basic physical properties you always want to know about compounds because it tells you how is it ionized or not ionized at various pHs. Okay, I have a couple of homework problems here I'd like you to take a look at. I'm going to go over a couple. Okay, first one, 1721. We're going to calculate the pH of a buffer that is 0.12 molar in lactic acid and 0.11 molar in sodium lactate. So we want to know the Ka and the pKa values. So the Ka value is 1.4 times 10 to the minus 4. That's the Ka for acid dissociation constant for lactic acid. If we do minus the log of that, then that's pKa, and that value turns out to be 3.85. We have a buffer solution, and we want to calculate the pH of it. So we can use that Henderson-Hasselbalch equation. That's pH equals pKa plus the log of the anion concentration divided by the acid concentration. And so we know the acid concentration is 0.12 molar, so that'll go in the denominator. And then in the numerator is that lactic acid, or the sodium lactate concentration, which is 0.11 molar. So we fill that in to our ratio there and take a log of that, and then we add that to 3.85, which was our pKa value that we calculated, and we get a value of 3.81. So calculating the pH of that buffer solution is pretty straightforward if we remember to use this this Henderson-Hasselbalch formula. Okay, then in part B, calculate the pH of a buffer formed by adding 85 mils of 0.13 molar lactic acid and 95 mils of 0.15 sodium lactate. So we have our buffer, we have volume and molarity. We know that our concentrations for our acid and then the conjugate base have to be in moles per liter, right? So what we need to do is we need to take each of these amounts, this mils of a certain amount of molar solution, convert those into molarity. So we can do that. Let's do the lactic acid first, is we're in mils, molarity is moles per liter, so we need to be working in liters. So 85 mils is equal to 0.085 liters. We multiply that times the molarity, 0.13 moles per liter. Now our numerator is in moles. The denominator will be total volume. So we have our 85 mils of the acid, 95 mils of the lactic acid ion, and then we can convert those into liters, so we have 0.085 liters plus 0.095 liters. That gives us our total volume. We do that math and we get a molar value for lactic acid. To get the lactate ion, we do a similar calculation. We convert its mils into liters, multiply by its molarity, and then divide by that total volume and get 0.079 molar lactate ion. Then we've got that, then we can use our Henderson-Hasselbalch equation. We already calculated out what the pKa was. So that's this 3.85 value. And then plus the log of the ratio of the anion, 0.079 molar, divided by the acid, 0.061 molar. We do all that math and we get a value of 3.96 as the pH. Okay, let's look at 1741. So in 1741, we want to know how many milliliters of 0.0850 sodium hydroxide are required to titrate each of the following solutions to the equivalence point. And the first one is 40 mils of 0.09 molar nitric acid. Okay, so we want to know how much base we have to add to get it to the equivalence point. Sodium hydroxide is a strong base, nitric acid is a strong acid. So we're going to have one of the equivalence pH 7 type titration curves. So the first thing we want to do is let's figure out how many moles of acid do we have present. Just as in the previous problem, we said we have to be working in moles and liters. And we're given 40 mils as our start. So first thing is let's convert this 40 mils into liters. That would be 0.040 liters. We multiply that times the molarity, 0.09 moles per liter, the liters cancel. That tells us we have 3.6 times 10 to the minus 3 moles of the nitric acid. We know the reaction is 1 mole of hydroxide to 1 mole of HNO3. So we can use that 1-to-1 mole relationship to go from moles of nitric to moles of hydroxide. Then we can use our molarity of the hydroxide that we're titrating with, in this case, 0.0850 moles per liter. The moles will be in the denominator, so the moles of hydroxide cancel out moles of hydroxide and leave us with mils of NaOH. Notice that when we wrote the molarity, we have moles in the denominator and 1,000 mils in the numerator. Because remember, 1 liter equals 1,000 mils. We wanted it expressed in mils. We do all that math and we get a value of 42.4 mils of sodium hydroxide. Okay, so in B, we have, okay, I'm going to skip B. B is very similar to A. I'm going to go to C. And in C, we have 50 mils of a solution that contains 1.85 grams of HCl per liter. Okay, so what's a little different about this problem is we're not giving them moles or we're not giving them molarity, we're giving grams. If you see that and you know you got to get into moles, you should be thinking, I have to calculate a molecular weight because I'm going to need that to switch from grams to moles. So we have our mils into liters, 0.05 liters. We know it's 1.85 grams of HCl per liter. So now we're in units of grams of HCl. This is where we're going to use our molecular weight of HCl being 36.5 grams per mole. And that molecular weight value allows us to then change that grams of HCl into moles of HCl. We then know 1 mole of HCl reacts with 1 mole of sodium hydroxide. So now we're into moles of sodium hydroxide. Then similar to what we did previously, we use that concentration, that molar concentration. In this case, we're trying to get to milliliters. So we're going to use 1,000 mils in the numerator, moles in the denominator. And then if we do all that math, we see it's 29.8 mils of sodium hydroxide. So some of the basic concepts here are we're working around with moles and grams and things like that. We're making sure our volumes are in the right units, whether that be mils or liters. And then we're using conversions in those. So on these kind of problems, I think if you write it out, keep your dimensional analysis straight, you'll probably be okay. All right, we're going to move on now to solubility equilibrium. So ionic compounds we know are strong electrolytes. And so because they're strong electrolytes, they dissociate completely, right? That was our definition a while back of what a strong electrolyte is. We can write equilibrium expressions just like we've been writing all along for this. Okay, so you think of it as if you have a solid and it's a strong electrolyte, or whether it's an ionic compound, it's going to dissociate as a strong electrolyte. And so the products are those cations and anions that it's dissociating it into. The reactant, think of it as that solid material. Remember what we said, if something's a pure solid, what do we do with it? We call it 1 and don't put it in the equation, in the equilibrium expression. That's all we're doing here. We give it a new term though, we call it the solubility product constant, KSP. But even though it has a different name, it's still the same idea on these equilibrium expressions, okay? KSP, the solubility constant, is just what is used for that dissociation of the solids into solution. But like I said, don't let that confuse you. All it's telling you is that this is just another equilibrium expression. Because you're starting with that solid, its value is 1, and just like we said, water as a pure solvent doesn't show up. Solids, we also said, doesn't show up because the value is 1, and so we don't put it into our expression because it doesn't impact that equilibrium constant value. Okay, so let's just take an example of how you would write this KSP expression. So the first example, we have barium sulfate, and we know it's a solid because it's got the little s in parentheses there. And then we have barium plus 2 and SO4 minus 2. Those each have the little AQ in parentheses, so that's telling us it's in the solution. We've got those ions there. If we think of writing equilibrium expressions as products over reactants, we have barium plus 2 concentration times sulfate concentration. The coefficients in front of each of those are in our reaction, there's 1, so there's no coefficients on the concentrations. The denominator would be barium sulfate solid. Well, that's a 1. It's a solid, so it doesn't impact anything, so it doesn't show up in our expression. So there's our equilibrium expression. In this case, it's a KSP because it's the solid dissolving. But really, the way you went about figuring it out is exactly the same as what we've been doing all along. Then let's look at the next example, barium phosphate. So this one's a little bit different because now we have 3 moles of barium plus 2 and 2 moles of phosphate, PO4-3, in solution. So when we write this equation, we have the barium plus 2 concentration times the phosphate concentration. But notice that we have to, on the barium, raise it to the power of 3 because of the 3 in this balanced equation. And the phosphate is raised to the power of 2 because that phosphate has a 2 in front of it in the balanced equation. Once again, on the reactant side, the barium phosphate is a solid, so it doesn't show up in this because it has that value of 1, so it doesn't impact the equilibrium constant, so it's not in there. Once again, similar to what we did before, we have our equation, make sure it's balanced, and then look for what's the reactants and the products. The products go on top. Because it's a solid, there's nothing in the denominator. And then we look to see what coefficients are for those products. In this case, we had a 3 and a 2, so we had to raise those concentrations to those powers. Okay, so there's a subtle difference between solubility and solubility product. So KSP is not exactly the same as solubility. When we talk about solubility, we're talking about quantities. And so that's why you'll see solubility expressed perhaps as grams per liter, so some weight per volume, or perhaps moles per liter. So you're talking about quantities. The solubility product constant, the KSP, what that's telling you is more or less how much of it would dissolve. It's not telling you the concentration, it's just telling you what, I think it is kind of what percentage would dissolve. And so if you have a real small KSP value, that's telling you that only a little bit of that solid would dissolve. Now, if you wanted to know what the saturation level was or something like that, you'd have to figure out the solubility where you have a weight volume or moles volume value. So KSP is actually, in my opinion, probably the more valuable thing than that saturated number. Because that saturated number, it's a little tricky to actually figure those out. The KSP values, you can look those up in tables, and it gives you a feel for, if I have something, how soluble it is. Is it gonna go much, very much gonna dissolve? And that's important to know. So small KSP value means only a little bit of it dissolves. The bigger the KSP value, the more it dissolves. And that makes sense, because remember, KSP is products over reactants. If the number is real big, it means you formed a lot of products, which means a lot of it dissolves. So if you keep that basic products over reactants logic in your head when you're doing this stuff, I think you can a lot of times figure stuff out even if you don't remember it off the top of your head. So let's take a look at calculating some solubility information from a KSP value. So in this case, we have calcium fluoride, and we're told that the KSP value is 3.9 times 10 to the minus 11. So right now, if I look at that and I see 3.9 times 10 to the minus 11, and I say, boy, that doesn't dissociate much, okay? Because 10 to the minus 11 is a pretty little number. But we'll go ahead and write this out. So calcium fluoride dissociates to calcium ions, which are +2 charge, and fluoride ions, which are -1 charge. To balance it, we need a 2 in front of the fluoride. And so then when we write our KSP expression, we have that calcium ion concentration times the fluoride ion concentration and the fluoride one has to be squared because of the 2 coefficient out in front of the F minus. And then that, of course, is equal to the KSP value. Well, what do you think is going to be next? We're still going to have one of our little tables, even though it isn't totally applicable, but we like this format. This helps organize things. This is our friend. So the calcium fluoride, you'll see, because it's solid, it doesn't participate. So it's just kind of a dummy there. It's just a placeholder. We have our calcium plus 2 ions. We have our fluoride ions. Initial, none of those. We just have that chunk of calcium fluoride. And then we have some change, and some amount of calcium is going to dissociate. Some amount of fluorine. So fluoride ion. It's 2x because we go back and look at our stoichiometry on our problem, and for every mole of calcium plus 2, we get 2 moles of fluoride ion. So that's why we have plus 2x in the change box for fluoride ion. And then at equilibrium, calcium is going to be that x value, and fluoride is going to be 2x. So now we can use those values to plug into our KSP expression. Our KSP value we can get from a table, and we can see it's 3.9 times 10 to the minus 11. X was that calcium concentration. 2x, excuse me, was the fluoride concentration. That 2x has to be squared. We do all that math and we get 4x cubed. We solve for x and we get 2.1 times 10 to the minus 4 molar as that concentration values that we were seeking. Hopefully nothing there was too strange to you, but I will point out one thing on this problem that make sure you know how to do is, if you have 4x cubed equals 3.9 times 10 to the minus 11, do you know which buttons to press on your calculator? Because you're finding a cube root there, okay? I'm not certain if we've had to do that yet this semester. So if you get a problem like this, first thing, of course, you divide it by 4, but then you have x cubed equals roughly 1 times 10 to the minus 11. So you find the cube root of that. I don't know about you, but I can't do that in my head. I would need my calculator to do that. And so make sure you know on your calculator what buttons to press if you get a problem like that. All right. Let's talk about solubility a little bit. We kind of started this chapter, we said one of the things that affects solubility is something called the common ion effect. And if we look at this graph here, you really get a feel for what common ion effect is. And think of that KSP expression. KSP equals concentration of the 2 ions that solid is dissociating into, right? Pretty simple. The K value never changes. It's a constant. By definition, it's a constant. So if you have these 2 variables and one of them goes up, well, then the other one's got to go down in order to have that product still equal the K value. Well, if one of those goes down, then that means the equilibrium had to be pushed back towards the solid. That's the only way to get rid of it, right? And that's what we're talking about when we say common ion effect. It means if you introduce one of those ions that's in that KSP expression, it's going to decrease the solubility. In this example, in this plot here, we have calcium fluoride, CaF2, and we see that in just water, it's between 10 to the minus 4, 10 to the minus 3 is the concentration. Then on the x-axis here, we're adding some sodium fluoride. So in other words, we're adding the common ion here would be the F minus ion is being added. So as that concentration of the fluoride increases, in other words, we add more fluoride to it, it's pushing that equilibrium back to having less of the calcium fluoride dissolve. And we see that. We go from 10 to the minus 3, 10 to the minus 4. Now we're in the 10 to the minus 6, minus 7 range. Then we're 10 to the minus 8 range, 10 to the minus 9, to where finally we're just about at 10 to the minus 9. Not very soluble as you add more fluoride in there, because you push that equilibrium back to, think of it as pushing it back to the reactants. In this case, the reactant is the dissolution of that calcium fluoride. So let's go ahead and do a calculation. When you have a common ion, so we're being asked, what's the molar solubility of calcium fluoride? And we have 0.01 molar calcium nitrate. So in this case, calcium is the common ion. We write our equation out, calcium fluoride solid goes to calcium plus 2, and then 2 moles of fluoride ion. Based on that equation, we write our equilibrium expression, calcium plus 2 concentration times fluoride minus concentration. Because of the 2 coefficient in the formula, we have to square the F minus concentration. And then we can look up our KSP value for the calcium fluoride, and that's 3.9 times 10 to the minus 11. So now we have our expression. And we know we've added 0.01 molar calcium nitrate. So we'll have our box again. Because it's a solid, the calcium fluoride doesn't participate in this. But we're told that the solution is 0.01 molar calcium plus 2. And before any dissociation of that solid has happened, the fluoride is 0. So then let's see what our change is. We're going to have some change. That's the dissociation of the calcium fluoride. So that's plus X for the calcium and plus 2X for the fluoride. The 2X comes from, once again, the 2X comes from the stoichiometry of our reaction. 1 mole calcium, 2 moles fluoride. And then let's go ahead and then figure out what our equilibrium concentration is. Well, for the calcium, we started with 0.01. Then we add some amount, which we're calling X, from the dissociation of the calcium fluoride. We did 0.01 plus X. The fluoride ion, we started with none. We picked up 2X, so that's 2X there. So now we can plug those values in. We can plug those values into our KSP expression. So our KSP value equals 0.01 plus X times the quantity of 2X, that quantity squared. Well, we're going to assume, and we'll see in a moment here if it's a good assumption, but we're going to assume that this amount of X that is gained relative to 0.01 is not very significant. So to make the math easier, we're going to just ignore that plus X. And that makes it then our KSP value of 3.9 times 10 to the minus 11 times 0.01 times that 2X quantity squared. If we solve for X, then we would have 3.1 times 10 to the minus 5 molar. Pretty small number. We go back and check it with regards to our 0.01, and we see that if we did add that to us, it really wouldn't impact it. It wouldn't show up in our significant figures at all. So it was a good assumption that we made there. So there's an example of doing a KSP calculation to see what the impact is on the concentrations when you have that common ion effect. So pH also impacts solubility. And this goes back to the pKa value that I was talking about earlier, is that if you have a basic anion, for instance, it'll be more soluble in an acidic solution. compounds want to be at their pKa. That's the equilibrium value, right? And so if you think about it, just think about yourself. You like to be super happy or super sad? Well, maybe sometimes, but for the most part, you like to be in equilibrium. You like to be just kind of your normal, going about your day type thing. Same for the molecules, and their equilibrium constant tells us what that is. And that pKa value is, as we know from the Henderson-Hasselbalch equation, related to pH, right? And so by changing the pH of a solution, you can affect the solubility, because if you're deprotonating something, if you're deprotonating an acid, protonating a base, then those forms are in general more soluble than the ones that aren't, either haven't picked up the proton or haven't donated the proton. Remember we talked, I think there was maybe 2 classes ago, where we talked about Lewis acids and bases, and I said, okay, you want to know about it a little bit, but we're not going to spend a lot of time on it. We are going to revisit it just for a moment here to talk about those metal ions again in that Lewis acid type of environment. The metal ions, we said, could act as Lewis acids and form complex ions with Lewis bases in the solvent. And what this does is these complexes can increase the solubility of some salts. So we're going to take a look at what that means here. Here are some examples of metal complexes. And so over here on the left, you see various metal complexes, some silver ones, aluminum, cadmium, chromium, cobalt, etc. We see the formation constants. And what I want you to see is some of those formation constants are really big. We've got a 10 to the positive 33. We've got a 10 to the 29. We've got some big ones. That means that that complex, that metal complex really is favored, right? Because remember, once again, products over reactants. If those equilibrium constants are big, it means the products are really favored. So some of these are pretty favored. And so you can see how having that, taking advantage of that formation could help get some things to dissolve by leveraging how favorable it is to form these metal complexes. These are just some more metals. You can see some other big numbers here. You see a 10 to the 35th and 10 to the 42nd for the 2 iron complexes. So those are really favored. Don't know how often you would be working with cyanide, but that's what CN is cyanide. And here's an example of how that would be used. So silver chloride, AgCl, is insoluble. It gives you a KSP value of 10 to the minus 10th, but essentially it's insoluble. That's actually a real common titration, is to determine how much chloride is in a solution. You titrate it with silver, usually it's silver nitrate. And you do that titration, and it's a potentiometric titration, so you measure the potential of the solution. And you can figure out how much salt is in something. It's a pretty classic titration that people do all the time. But it's based on silver chloride being a solid. Notice I said that it's usually silver nitrate that you use. The other thing you do is you acidify the solution. And the reason why is we see here what happens if this silver chloride is in the presence of ammonia in this case. We get a complex, a silver ammonia complex that forms. And so what it does is that complex solubilizes something that was essentially insoluble. So if you were doing a titration, you had a lot of ammonia in there, your titration is not going to work because this is going to override it. And you're going to start forming this silver ammonia complex here. And so this is just one example of where if you, in this case, didn't want that silver chloride precipitating out, you could put it in, you could add ammonia, make the solution basic, and then get this ammonia complex forming and reduce that precipitant. Okay, when we say something is amphoteric, it means it's soluble in acids, strong acids or bases. And so that means they can act as either acids or bases. And so there are some examples of that. That's all I'm going to say about that. I want to get to this part here about precipitants forming. So KSP, as I said before, is used to predict if something's going to precipitate out. It can be used to determine if something's going to precipitate out or not. And remember when we were talking about equilibrium expressions before, equilibrium constants, we did a calculation for something called Q, the reaction quotient. So you also can use that same calculation just in the context of KSPs to see if the solution, if the system's in equilibrium, to see if you can put more solids in, or see if a precipitation is going to occur. And so if you go ahead and calculate it and Q equals the solubility constant, the KSP value, then you're at equilibrium and the solution is saturated. If Q is less than KSP, okay, so if it's smaller, that means you can have more products, right? And so that means you can put more solid in and dissolve more stuff. If Q is greater than the KSP, then that means you're going to have a precipitation happening. Okay, so once again, that Q is calculated just as you would calculate a KSP, but it's just using the concentrations that you have at the time. And we'll go over an example of that in a moment. Another thing that I just want to mention briefly is what they call selective precipitation of ions. And so sometimes you can have various ions all in solution, and by adding a particular ion, you'll get some of the ions to precipitate and not others. And where that really comes into play is qualitative analysis of ions. This is something that a lot of Gen Chem labs do. I don't think you guys are doing this semester, but I'm not certain. But this is where you get an unknown, it's usually some kind of metal cation, and then you go through this decision tree, so to speak, this flow chart, where you add things, and like for instance here, you add 6 molar HCl, if you get a precipitation, then you know it's a group 1 insoluble chloride. So it could either be silver chloride, lead chloride, mercury chloride, and you keep following this down. And if you do it properly, you can usually figure out what it is. It works kind of okay. I think it gets done less now these days just because there's a ton of other ways that people do this that's a little bit easier. But this is the idea behind having things in solution, adding something that will precipitate some of the ions, but not all of them, and you get some information about what those are. I wouldn't worry about this too much. It's just kind of an interesting chemistry exercise. I do want to just spend a couple minutes here before we finish up on a couple homework problems. The first one, 1751, writing the KSP expression. So over here on the left, we have the compounds. On the right, the expression. Don't worry about the last one, the Hg2, Br2. That's a really weirdo one. Don't even spend 1 second on it. But the first 3 do. So for silver and iodine, that one, KSP would be the silver ion concentration times the iodine concentration. It's 1-to-1 in terms of the moles. So there's no exponents on those. Same on strontium sulfate. You have strontium ion, and then sulfate anion. And then finally, the third one, ferric oxide, you have iron +2, and then hydroxide. Because there's 2 moles of OH going with that iron to make the charge balance, you have to square the hydroxide. So once again, writing those kind of expressions, very similar to what we did before. If you wanted to write out the whole equation, you certainly could. But make sure you're comfortable writing those kind of expressions. Okay, let me just briefly look at this number 55. And in 55, you have 1 liter solution saturated with calcium oxalate, and it contains 0.061 calcium oxalate. calculate the KSP for this salt. So here we know we have a gram value. What we say before, if you have grams, you're going to have to get it into moles. So up here, I've calculated my molecular weight for calcium oxalate, that's 128. I can then convert that 0.0061 grams into moles. It's a 1 liter basis, so that's the molarity as well, 4.76 times 10 to the minus 5. I know from my reaction that for every mole of calcium, I get the same number of moles of oxalate. So what that tells me here is 4.76 and 4.76 times 10 to the minus 5 are the concentrations. I multiply those and I can get my KSP value. (1769). Take a look at that problem. You're going to calculate the Q value and then compare it to KSP. And so in this first one, you kind of go through the calculation. You see KSP, which you can look up in Appendix D3 in the book, textbook. KSP value 6.5 times 10 to the minus 6. The Q value was 10 to the minus 14. That's a lot smaller than 10 to the minus 6. So that tells me there's no precipitation going to occur. I can have more products being formed, okay? Take a look at those, take a look at the other homework problems. And just a reminder again, Thursday exam on chapters 15, 16, 17 will be posted in Canvas. Take it during class time. And that's it for today. Thank you.
Almost time for a nap.